Good morning. This is Deep Generative Models, and this is our week 13. In this week, we are going to talk about the following topics. The first, we are going to talk about our last homework 5. It is using the DreamBoost to fine-tune or to customize a diffusion model, stable diffusion model. We are going to talk about just a little bit later. Secondly, we are going to talk about two image generative models. One is MUSE, which I think it is very interesting, and this approach might be promising comparing to the diffusion model or flow matrix model, though it is still not considered to be the SOTA yet, but we should keep an eye on it. And another one is the LCM model, which is the latent consistency model. This one has been widely used already because it can be accompanied with the diffusion models or the flow matrix models. Okay, so the major purpose of this model is that it can be used to speed up the models, diffusion models. It can be used to speed up diffusion models a lot. So we'll see it in a while. And lastly, we are going to talk about the multimodal large language models. There are a lot of application of language models, large language models, and currently the trend is on the multimodal large language models, including like GPT-4o and Google's Gemini Flash and Project Astro. And also Microsoft just announced its Copilot Plus PC. And yesterday I see that the Meta released their latest multimodal base models. So it is currently perhaps the most trending approach or topics in deep learning or in AI. So let's start with the homework. The purpose of the objective of this homework is to use DreamBoost to customize your own diffusion models. So you need to create your own data set and customize by fine-tuning the stable diffusion model using the DreamBoost method, which we have covered in previous lectures. So here are some instructions. You can find it in our lecture website. So the main point is to familiar with the process and preparing the dataset itself. We are not focusing on the coding itself because it may take a while if you wish to familiar with the algorithm, and you may need to have some trial and errors before you can actually write the correct code to implement the training algorithm. If you are interested in to do so, you can do that, but I'm not expecting everybody to do such complicated work. So I'm asking you to focusing on preparing the training data and run the existing code from Hugging Face. So Hugging Face provides a diffuser library. It collects a lot of different algorithms and code. You may refer to this URL and finding the instruction and the description of the DreamBoost implementations in the Hugging Face diffusers. So you can use the code and the instruction here. You can find the training code right here. And also, because we are going to present, and you should upload your result in notebook format. So in next page, you will see that there are also some notebook references. There are several variations or flavor for training the customized diffusion model with DreamBoost. Like you can either train it with or without LoRa. And you can choose your different base models like SDXL, SD 1.5, 1.4, or SD 2.0, 2.1. It's up to you. You can choose any one of them. But you should provide or prepare your own customized training data. So there are many different topics or objects or concepts you can use for the theme of your DreamBoost fine tuning. Like you may wish to train it for a specific character or some certain style of some artist. It's all up to you, but you have to prepare the dataset yourself so that you can understand the format of the dataset. What kind of information should be provided in the training dataset. And you may also see the effect of a number of examples or number of samples in the dataset, and the effect of the training epoch or training steps affect the qualities of generated images. Okay, so you can find the instruction and the code from here. Here you can also check the notebooks. So in this slide, you can actually click and to go to the repo and see the notebooks. There are 4 notebooks related to DreamBoost. Some of them are for the SDXL DreamBoost LoRa. There are 2 of them. One is advanced example, and the other is the without advanced. It's just an example without advanced. And there are also 2 notebooks for SD Stable Diffusion DreamBoost. One is for training, one is for inference. In the SDXL examples, they are just simply calling the training script that is provided here. So if you go to the notebook, you will see that it download the training script and coding the training script using accelerate. You should see that calling a command called accelerate launch and launch the script, so it can train it in multiple GPU or in distributed environment. And the other one is using the without XL. It's just maybe like 2 or 3 years ago. Notebook from 2 or 3 years ago. It's the original examples in Hugging Face notebooks. It actually contains the training loops in the notebooks. You can use that also, and it actually helps you to understand more about the training procedure because it already write in. So everything is coded in the notebook. You can choose them either way because our focus is on the preparing of the dataset. The interesting thing about the SDXL advanced example is that the way that it how it prepare a data set, because we need a image and a text pair samples in the data set. So how do you generate the text corresponding to an image? So one way to do that is you have a template, just saying, okay, this is a photo of something, a picture of something, and you can replace the something with your concept, your name, or your specified token, specified spatial word with something. So that's fine. That's one way to just have a template of sentences and corresponding to each images. But in here, in the SDXL advanced example, it uses Blip, which we are talk about later. It is a multimodal. You can consider it as a text image model that can generate a caption, can generate image caption from an image. Either way, you can do it either way, but the key point is you have to understand what kind of information you should provide to the training data. And after you know what information you should provide, then you can find a way to provide the information, to generate the information. So either using template generation or using a multimodal model like Blip. Either way, you can do that. Okay, so here is some. Here's the list of requirement. The requirement. You should generate it in a notebook format, and I would suggest you that you use to run the training on a GPU. Do not run it on a CPU. It may take too long. It is doable, but it kind of defies purpose because everybody do it on a GPU. So you have a different feeling about what it is. It is supposed to be a fast procedure. Like you should do it in 1 or 2 hours. You can do it in 1 or 2 hours and you can see some results. So you can use code in the notebook that we have provided the link here. That is collected in the Hugging Face notebooks. You can use that. That is totally fine. However, you should expect that you are going to modify the code because you have to install some packages, Python packages, and these notebooks may not do the perfect job. So because everybody has a different machine and different environment, you should read the notebook if you encounter any issues when installing packages. Also, that's something you need to expect it to solve it. Although this is not the main purpose of this course because we are more focusing on the algorithm and the flow of training, training flow, like how do you prepare a data set, how do you train it, what is the feeling of training it, and what is the models that you are expected to get after you fine-tune the model, how to use the model to generate new images, new samples. So every information passing through the whole procedures. That's the main point. However, because the reality is that you are going to use a computer, you are going to use a GPU. So you still need the ability to solve any technical issues. So one of the issues that happens a lot is the environment. You need to install the packages. So no matter what, you have to have the ability to overcome the issues of setting up the environment to run the code. So I'm not asking you to implement the whole algorithm, but at least there are some difficulty you need to overcome for installing the packages, so that you can actually run the code on a GPU environment. And secondly, you need a GPU. Not everybody owns their GPU computer or have free access to their like the lab computers or have enough GPUs. However, everybody can have access to some free GPU service like Colab and Kaggle. So you should, if you don't have already have other resource or access to GPU for training these kind of things, you can use Colab or Kaggle. Okay, so here are a list of requirements of homework. So, which means what you should present it in the notebooks that you submit in the upload to the E3 server. One is that you need to show the dataset that you just created. So that is one thing that you should have show some creativity or at least show some evidence that you actually create this dataset, or not just copy from. You should not just copy an existing dataset, because in the example it will definitely download some dataset from some Hugging Face repo or something like that. You should always create your own dataset, collect your own images, and show how you generate the text. Either, like I said, maybe you generate using a fixed set of template, or you use a deep learning models, or language model, image capture models. So in the example, it uses Blip, but you can use other. But anyway, you need to generate the text corresponding to each images. That is one issue. You should not just say, okay, I collect some images and magically there are some text corresponding to this image. That is something you need to explain. There are many ways to find the text corresponding to the images. So for example, if you crawl the images from a website, maybe because in HTML, each image has a ALT text, alternative text. Maybe that text is good enough. If that one is good enough, then you should let us know. Or maybe in the website, it already contains some description of its image, not in the ALT text, but maybe in a table or in a div, maybe. But you need to let us know how you generate the text in the notebook. Also, that is one key point. And the other thing is that you need to show that you actually do the training. This one might be just easy if you already do it. Well, I'm not asking too much, but when you do the training, it will show some text output. If you're using the accelerate launch the script or running the training loop in the notebook, it will definitely show some progress bar or some, okay, the training begin, the training end, something text output. Just show that. That's good enough for me. And finally, you have to demonstrate that the models has already trained it. So you should use some text prompt to show the images generated by the models. You need to let me know what is the prompt, text prompt that you are using, and what is the spatial keyword that. So because we usually related a spatial keyword to the concept. So what is the spatial keyword or token that you are using? And when generate the images and the samples, although you can simply just randomly select some random prompt that contains the word, or just using the prompt in the dataset. But I strongly suggest you to refer to this web page and see how they try to emphasize their work. They're using some specially designed, or at least they considering. They are not just using some the prompt from the dataset. They're trying to use their newly because we have a spatial token like here. It should be like this one is for a dog. Maybe they use a spatial token like a V dog. So it tried to test how well this new concept work along with other styles. Also, you may see that here it tried to, although it is trained on a specific design of a clock, it tried different fidelity or in new context, and try different just to play with your customized models and see how what is the capability it can reach. So I would suggest you that you should try this sort of prompt to demonstrate how good or the limitation of your model. Okay, so that's it for the homework. Let's start with the MUSE model. MUSE is it is also a text-to-image generative models, but from the name, it is using a masked generative transformer. It is from Google research. I remember there are like two models, two researches that are related in this approach, but I'm not sure. I forget this one is the first one or the second one. But we'll see this one, the MUSE. So it is also a text-to-image generative model, but the difference between this one and the diffusion model is it is trained on a masked modeling task in discrete token space. So that's a key difference. The diffusion model is usually training on latent space or on no matter on latent space or on pixel space. It is training on a continuous space, or not a discrete token space. So that's the first difference. And the second one, it is training on a masked modeling task. The diffusion model is training on a denoise task. This one is training on a masked modeling task. Although you may feel that mask is kind of a noise, but when we talk about diffusion model, we are usually talk about the Gaussian noise. So this kind of noise is very different. And for the second part, the discrete token space, it is more like the VQ VAE or VQ GAN that we were talking about. So this model, in my opinion, is more related or more similar to the VQ GAN model. So given a text embedding extracted from a pre-trained model LLM, the MUSE is trained to predict randomly masked image token. So this kind of these two segments summarize how it is trained. you should we can get a rough idea of what is this model is. So it is text conditioned, and we are not going to modify or adjust the large language model. It is fixed, and we are getting the text encoding from the language model. And then we should treat the text encoding as a condition. And we use this condition to train a demask model. That is, given a mask, we are going to guess what is the token being masked. So this is like the language model, like the BERT we were talking about. When we discuss about the language models, yeah, encoder, decoder, or the decoder style models. There are 3 different kind of training. The GPT is the decoder, and for the BERT, it uses a mask. It masks out some tokens and try to predict the mask tokens. Okay, let me go to the next page. So another famous result for this mask training paradigm is the mask autoencoder. This one is one of the very well-known pre-training method for using a transformer on featuring task. So this one is a mask autoencoder. Basically, we are masking out, by giving an image, we are masking out some of the, we find different patches. First, we split the input into different patches. And some patches are masked out. So the model is not going to get the information of the gray out patches. It only gets the patches, small patches. And because we are going to train an autoencoder, so this encoder taking these inputs and get encoding and try to decode to reconstruct the original image. So this can also viewed as a denoise autoencoder, just like the diffusion model, but the noise type is very different. We corrupt the image at the beginning and try to reconstruct it. But it uses a totally different way to corrupt the original input. You may think that there are some flavor of these or variations of this type of training. First of all is, should we let the encoder know the position of these patches? The most the straightforward approach might not, might just, because this one is masked images, so the encoder should definitely get the position of which this patch is. Sorry. But on the other hand, it sort of looks like a puzzle, right? Like we are playing a puzzle, only it is a subset of puzzle. So because human being may find it interesting to complete a puzzle game. So maybe this is interesting also for training a model. So we should consider another approach that does not contain the position information, so that we can treat this as a puzzle. and let the model to influence the position of these small patches. Another consideration is, let me summarize a little bit. So both approach is reasonable, and you can see the paper to see what approach it takes. And another consideration is what is the ratio of the patch that we should mask. Should we use a fixed ratio, or should we randomly vary the ratio of mask patches when training? Also, that's another consideration. You will see very soon that we'll go to that when we see the page. So just keep in mind, it is you can choose you should make some decisions about which page should we mask, how many, or which page should we mask out when we do the training. Also, there are many different considerations. Okay. So there are some advantage of this MUSE model, a masked generative model. It is more efficient due to the use of discrete tokens. As it claims that because it uses discrete tokens, so it is more efficient and require few sample iterations. And it also claims that it directly enables a number of image edit applications. Also, we'll see it very soon. Here are some examples of the text and generated corresponding generated images, so that you can have a feeling of how good what is the quality of the image generated by these models. It is fine. It is fine. May not be sold up, but it is totally fine. But the thing is, because it is using to complete the image from some mask out things, so it can naturally have several applications like inpainting. Because inpainting is simply, if we consider these patches, these are the patches that has been masked out, grayed out. So the model is trained to complete these masked out things. So it is very natural fit to do the inpainting process. And it is also natural fit to do the outpainting process, because we can simply consider the outside things to be gray out, and the model can predict what is on the gray out patches. And also it can do mask-free editing. So that's another thing, but it can do so. Let me go back to the selection of the mask when we do the training. So if this is the sort of the application that we are aiming for, then maybe we should not only consider the random mask pattern. We should also consider things like this one, like we max out something that in a rectangle in the middle, or like if we are considering other outpainting, we should also consider the mask like this one. So then I'm just saying that we should consider when we do this kind of mask denoise mask autoencoder things, you should make a decision about what is a mask we should use when we do the training. even if you don't do the decision, you have already do a decision because you probably use some. I mean, you have to let the training loop to generate some mask anyway. Even you don't realize you are making a decision, you are already making one. It's just you're not decide it in a more intelligible way. You just because you are not aware of other choice. But when you do the mask autoencoder things, the training, it is always a very important thing to decide the mask. What is the mask should be. So have to aware of it. So this is the architecture of the MUSE framework. Because it uses a VQ tokenizer, it has to be tokenized beforehand. So it is naturally fit. You should consider the architecture like a VQ game or VQ VAE because we have to do the tokenization. And we already know that another way to do the tokenization is like this one, like the mask autoencoder or VIT. You do the patch and like the paper VIT, we do the patch tokenization. So that you can also do the things like pixel CNN. So each pixel you have 0 to 255. From 0 to 255. Each pixel you have a intense value of gray value. So you can do that pixel wise, like pixel CNN or pixel INN. But it is more popular to do things like either like the way that the VIT does, using patches, or we should do the VQ tokenizer. In MUSE, it uses the VQ tokenizer. In fact, it train a VQ game before it pre-train a VQ game on a lower dimension space, like 256 by 256. So it train these guys, train the VQ tokenizer using a VQ game method to do that. And this is considered the pre-trained model. And we are going to frozen the tokenizer and then do the mask autoencoder training. So we got a VQ tokenizer, and then it does the masked autoencoder thing. To be specified, it uses a conditional transformer to do the mask autoencoder thing. So the input is a masked token. And we have a transformer here and reconstruct the missing tokens. So very similar to the mask autoencoder, but we have a text embedding as a condition here. So here we got a low resolution output, and then it also contains a super resolution transformer here. It takes both the low resolution reconstruction and the text embedding as a condition, and do the mask high resolution. Take the mask high resolution tokens as input and output reconstruct the high resolution tokens. So all of this working in the token space, and because it uses the VQ tokenizer, so it can be considered as in the latent space, just like the latent diffusion or stable diffusion. It is work in the latent space, but the latent space is discrete. It's discrete. And it also do something like denoise autoencoder. Although it may not need to specify a encoder and decoder, just like the UNet in diffusion model, but it is doing the denoising. Only the noise here is the mask. So that's pretty much about architecture of the MUSE. So what is the mask it chooses? So one key point is it chooses the different ratios. It varies the ratios of the mask out things in this mask. So sometimes it has a lower percentage of patches tokens being maxed out, and sometimes it is going to be higher. And I'm not aware of it using some rectangle or the inverse of rectangle, since that is specified for inpainting or outpainting. So it does not consider this kind of mask. But it does vary the ratio of mask out patches. So here are some details about the super resolution models. Okay, so you can see that how does this text embedding and the low resolution tokens are going to use as condition. Like what we were talking about the DIT. There are many, last week we talked about DIT and we discussed there are many natural ways to inject the conditions into a transformer block. Here it chooses the cross attention approach. And in the DIT, it finally chooses the modulated approach so that it modifies the gamma and the beta in the normalization layer. So it can be considered ADA layer normalization. But here it chooses the cross attention approach right here. But I'm hoping you, after taking this class and see different approaches, so you can mix and match different popular methods to serve your goal or your objective. But here we definitely can use the modulate approach. Both of them have some properties that we are assuming. So for the modulated approach, it's more like changing the style of these things. And for the cross attention condition, it's more like we use some combinations of use this as a raw material and using some using the raw materials from it. Then both of them have some properties that we are assuming, but in a more abstract way, there are both some ways to inject condition into the list block. So why do we need a super resolution? The explanation, it is explained in the paper, and it is, maybe you have already guessed it, because if you directly do the things in the resolution of a high resolution, it does not work well because it focuses on the low level details. So the structure of the image is not good. So we are doing it in a hierarchy way. From the low resolution, so the model can have a more correct structure of the things. Then the high resolution, super resolution models take care of the detail of the image. Low level detail, let's call it low level details. And also, not only it has two levels, the low level image and the super resolution part, because it is a latent model. So it actually works on a 60 by 16 latent space for low resolution scenes. So it has more hierarchy than like it's more like a three level hierarchies. And also it has a decoder fine tune, because we know it has an encoder and decoder, right? So it also do a decoder fine tune to further improve the quality of a generated image. For me, this thing is more like a last resort, because it is definitely works, have some benefit. If you wish to improve the quality of your stereo diffusion models, you can also do the same thing to fine-tune your decoder only. You don't need to fine-tune your encoder. You can fine-tune your decoder to make the decoder have to generate better quality images. But because this one is almost for sure, it will have some benefit. So we don't have to do this in early stage. We can put it keep it later for later use. For sometimes we are out of tricks, so maybe we can try it and to see what happens. So I will reserve it later, but it's used here, and we appreciate it. Discuss the result of it does on this MUSE model. And it used the variable masking rate, like I have discussed before. This is also very important for these masked models, masked autoencoder models, masked autoencoder style models. And it used the classifier free guidance. For this section in the paper, I think it serves a good example of showing how do we transfer a method from one algorithm into another. Because the original classifier guidance method is applied to the diffuser models. Although we have pointed out that there are some similarity in a more abstract way, that the MUSE and the diffuser model are pretty much the same, because they are working on the latent space, like the latent diffusion models, and it can be considered as a denoise autoencoder for each step. But still, there are different models. So it you can read it in the paper and to see their consideration about what is the usual consideration. At least for this case, when they try to apply a method from a different algorithm into their own. Okay, so that's the whole training process. But how do we actually do the inference? It is not obviously clear how do we do the inference. So when we see the title and see the abstract, this one is the most thing that I do not figure out at the very beginning. Because when I see when you see the description right here, like right here, you're probably already guessing most of the rest of the part, and you have already aware of the decision that you should make of over a step, like the ratio. How do you do the mask, and do you use the hierarchy? Do you has a latent? How do you use the VQ tokenizer like here, or using a VIT tokenizer, the patch tokenizer? So you already kind of have an idea of how it is going and the path and the decision point, how to implement the whole things. And you know that is most likely to work because everything is reasonable. But it is still not clear how to do the inference. Because right now we have something that is something like a max autoencoder. What we can do is appending, that is very nature. But how do we actually generate an image from scratch? That's the thing that is not totally clear. So that's the interesting part. So here are some assumption or consideration they are thinking of. They want to do it parallelly to predict multiple output tokens at once. And they are doing things in several paths, not just in one path. And they assume they have observed a key assumption that many tokens are conditionally independent given other token. So what they do is, first the decoding is performed based on a cosine schedule, and they choose a certain fixed fraction. Also, this is decided on depending on the scheduling. So there are fixed fractions of highest confidence mass tokens at each step. So they predict some tokens at the first step, and then they keep this predicted things fixed and going to predict the next round, and so on. This seems not to be very I mean, at least this is not obviously this should work, but considering it only has 16 by 16 tokens, it's not that big. So this seems to be reasonable. So for the base model, it only have 256 tokens. Not much. And it used 24 decoding steps. So for each step, it only predict like, in average, it predict like 10 or 11 tokens. And for super resolution, it's doing it much faster because it already has a low resolution. I mean, for base models, it seems to be at least very promising because it only has like less than 300 tokens, and it uses a lot of steps to do a decoding. So we already know that if we do it in an auto-regressive way, it should just work. But it is not in an auto-regressive way. It only had 24 steps, but because it has a cosine scheduling, so it should just work. However, for a super resolution, because it has more tokens, so how if we generate it directly, it doesn't seem to work that well. If we imagine about the process, it just have too many tokens. But this kind of explains the observation that when using the when doing a high resolution, it only focuses on the low level details because it simply has too many tokens. It's very difficult to construct all of them in a more consistent way. But right now, we already have low resolution images. At least we have a latent of it. So you can imagine that here we can have a reference to these low resolution images, and of course we also have a text embedding. So I think it will definitely work because we already have a low resolution images, so it can refer to low resolution to see what we should generate at this small page. So after reading all this, it all makes sense and seems everything is reasonable and it should just work very well. my comment is it's extremely similar to the things that FeatureGain does, because FeatureGain also has a tokenizer, and except the middle part, it also using a transformer, but it is doing it in an auto-regressive way. But here it try to make it more efficient, so it's using a masked way to training the transformer, so it can generate more tokens at once. And because it is not that straightforward as a generative models, kind of like the BERT vs the GPT. So it actually has a 2 level. First level is low resolution, and going to the high resolution. And also, just like the FeatureGain, the feature part and the token, the feature part and the transformer part are doing it. They do it separately, train it separately. They first train the feature part, then they train the transformer part. That's the similar thing. So this one has some similarity with the FeatureGain, and also have some similarity with the diffusion model. So that's one of the interesting model. So here are some visualization of the generative procedure. So like we had mentioned, they have 24 steps for low resolution. Also, it shows the sum of the steps. And for a high resolution, at the very beginning, it already has something. You can see the whole picture, like a cat right here and some chessboard here. Unlike the low resolution, you haven't see anything. It is too vague right here. And you can see that the enhancement of the details. Okay, so that's the MUSE. And another generative model we are going to talk about today is a latent consistency model. This one is used a lot. This one has been used a lot because it can be considered as a fast way to do the sampling for stereo diffusion. So the selling point of this one is it can do the diffusion in just 4 steps and has a very high qualities. These are some examples of like when we do the diffusion model, we usually do some like 20-step sampling or maybe 30-step sampling. Originally, it will have like 1,000 steps of sampling, so it is very slow when we do the sampling. But for LCM, it can do it in just 4 steps. And for the first step, it already has some result, but the result is very blurred. And in the second step, it already has some passable qualities. And at the first step, the quality is achieve the optimal qualities for the LCM models. Because diffusion model has an obvious weakness is that it requires a lot of sample steps. So a lot of research are trying to reduce the step of sampling to accelerate the diffusion models. The first one is the training-free method. That is, you don't need to train the models using a different method. You're just using the already trained diffusion models. And we try to do something to speed up the sampling. So one way is using the OD solvers. to solve, like we say, the neural ODE. So maybe using ODE maybe can achieve a faster sampling. And using a different adaptive step size solver, so like a different scheduler things. And also a predictive corrector method is also very popular ways to do that. Another method to modify the training schedule, training algorithm. So we have optimized discretizations, truncated diffusions, neural operators, and also we can use decelerations. Because we already have diffusion models, so a lot of people are going to try to using a deceleration to decelerate a smaller model from a larger model to make it more efficient. So that's a very popular approach. Another approach is, instead of using diffusion, we try to modify or improve the diffusion model into something else. Like what we have already discussed last week, the flow matching algorithm, or like rectify flow. So this, they can use smaller sample size, sample steps. Also, this one is a rectify flow paper. So there's another approach to make it faster. So in this paper, it's more like a distillation. You can consider it like a distillation. The latent consistent model is come from the consistency model, and apply this method on the latent space. So we go back to the consistency model. This one is I think it's also from because these are OpenAI guys. They can see that OpenAI guys. So this one is also from OpenAI. The original paper, this one is working on the pixel space. So what is the consistency? What is a consistency model? Although this name seems to be deep, or sort of like maybe something very difficult to understand, very mathematical, the idea is pretty simple. You can see it already used something like a probability for ODE or things. The basic idea is that instead of denoise it step by step, why not we simply denoise it all the way to the x0. So recall that in the diffusion model, our model, when you give xt, will predict the xt minus 1. So why not we simply given xt or xt prime or x capital T, we simply predict x0 instead. So that's all. That's the consistency models. So there are two decisions we can do. There are two different paths in front of us. One is distillation. So suppose we already have a diffusion model. We can distillate the consistent model from a already pre-trained diffusion model. Another way is, should we just train it from scratch? So there are two obvious ways just in front of us. In the paper, they consider both of them. Okay, just one more note that what the LCM does, and you can just go to the YouTube and search LCM, or you can go to Google to search LCM Krita, and you can see a lot of videos that you probably have already seen it. somebody is drawing something on the screen, and it instantly have something more photorealistic or more artistic on the other on another half of the screen. So almost instantly, when you draw something, and it changes according to what you draw, very fast. Also, that's what LCM does, and that is probably what the impression of people get for LCM at the beginning. Just when you draw something, it instantly appears on an effect on the result of rendered by diffusion models. So it helps you to draw something really quick and get some good result. If you haven't tried it before, you can try it using the Krita. Krita. Krita is an open source drawing applications, sort of like Photoshop, but it's more focusing on drawing things. There are two Photoshop alternatives in open source. One is GIMP. It is more like a photo processing software, more like a Photoshop alternative. Although the UI is, people always complain about the UI is very unfriendly. But it is kind of like an open source alternative to Photoshop. And another thing that people always consider about is Krita. But Krita is more like a sketching app. It allows you to draw something on it. But very like Photoshop. Recently, they have a lot of plugins about it to use diffusion models to do the generative AI. There are many different ways to use it. One way to do that is the live mode. So you can draw something on a screen, and it will, using the thing that you draw on the screen as a reference, as a condition input, and it will generate images more supposedly to be more artistic or more photorealistic according to your drawing and some text prompt you were given. Also, that's very interesting. You should try it. And by the way, the backend of the AI is using Comfy UI, which we probably already mentioned it in previous, that the two popular, we give a demonstration of using Comfy UI. So two popular open source UI for diffusion model that you can host on your local machine is, one is the A1111 Web UI, and the other one is more I think has a bigger community, is the Comfy UI. So the Krita AI is using Comfy UI as a backend. So both the Web UI A1111 Web UI and the Comfy UI, they have an API. So although they are UI, because the framework they are using, they also provide an API access. So in Comfy UI, when you build a workflow, it can provide an API so that you can access the API using other application. So, just a comment that you should try it and see how LCM works. Okay, so let's go back to the algorithm of LCM. So basically, the idea is simple. Instead of predict step by step, why not just predict it all the way back to x0? So don't mind this, like the probability flow, PFODE. It doesn't matter. It doesn't really matter. I don't think it uses any spatial or any particular result or theorem for ODE. It doesn't use that much. It might use some. After I think a while, I think use some of them, but they are just small part in the paper. In the majority of the paper, it's just a diffusion model, but you go back all the way to the origin. That's it. So why does it call self-consistency? The reason is that no matter what time step it is, the f, because we're not going to denoise to the one step before. We are going to denoise to the original image. So no matter which one it is, no matter which step it is, the result should be same because they have the same origin. So that means the self-consistency. So this one is used in the laws. This property is used in the laws because we can use this one. The difference between them, we want to minimize the difference between two of them. And also, we design the function in a way that is more easy to satisfy this property. So we can design this f theta xt to be this guy. So when t is to be very small, it is going to be not change much because we have already very close to x0. So we don't need to change it too much. So the c skip is going to be 1 when t is going to be very small, and the c out is going to be very small when t is very small. So that we can utilize this design to be more easier to satisfy this property, and hence easier to consequence is easier to do the training. So this one is an algorithm. The paper considers both distillation version and to training it from scratch. So both of them provide an algorithm. The only difference is that here we have the diffusion models already, but because it is considered any probability flow, so it doesn't call it a diffusion model, it just called it prior or something. But the idea is same. And you can see the loss right here. Loss, this is loss. Loss is a difference. The d is a distance or the difference. You should just call it a difference. But the difference is measured in a way that we call a difference, a distance or a metric. The difference between this guy and this guy. So these two guys has different time step. So we use the consistency loss. One of the important things is that when we wish to apply it to the latent space, we need some condition. In here, we didn't consider about condition, the text condition. So in the LCM paper, the most important thing is it consider the condition into it. So you can see that it has a C, a condition here. But pretty much, it's just pretty much using the consistent modeling in the latent space. That is kind of trivial because it just works. But the thing is, LCM also provide a way to use the conditional guided to do to consider to also incorporate the condition into the formula of the consistency model. But they are still pretty much the same. You can see that the distance between this guy and this guy, because they have different time step, and we still have some consistency loss. And now we are mostly talking about although they have two algorithms, like we said here, we're mostly considering the distillation version. Mostly consider distillation version. And you can see that at the in the FID and in the CLIP score, the LCM performs best at the first step, comparing to other methods like different scheduling or different different distillation method. It performs best at the first step. So that's why it uses the first step. So the S steps doesn't improve the quality much, and sometimes it even get worse qualities. So the LCM shines best when it works on 4 steps. So here are some more examples of the first step LCM. They use different. They can use a different classify free guidance scales omega. We have mentioned it in maybe last week or in previous lectures. So when we can use different scales. Another paper about the LCM is LCM LoRa. It is simply training the LCM on LoRa. The benefit is it can work on a higher dimensional. And also, because LoRa is a simple modification to the original, a recent paper says that the LoRa forget less and learn less because it doesn't forget much about the original model, but it can, because it has a low rank, so it has lower capacity, so it also learn less. But good thing is it is more like a fine tune or fine adjustment to the original weight. So LCM LoRa makes a lot of sense because the original model already is already a denoise model. So I think the LCM or CM works well on distillation is because we are kind of piggyback on the original hard training diffusion models. It already does a pretty good job on denoising. So the original diffusion model is already a denoising model. So the LCM model is supposed to be very similar to the original one. It just need to denoise a little bit harder, maybe just that. So they are very similar. So LoRa makes a lot of sense on this situation. And also, because we know that a lot of customized models on the stereo diffusion models, like different styles or maybe specialize in generate some certain characters, like generate humans or generate some artistic styles. There are a lot of different customized stereo diffusion models available, either in a LoRa form or in a fine-tuned form. So if we are providing this in a LoRa format, there are two benefits. One is that we have already mentioned, because we should not change the model too much. So LoRa makes a lot of sense. We can train it faster, and because it is faster, it can work on a more higher resolution or more larger models like SDXL. So that's one thing. The other thing is that it works well with other LoRa or other customized models. So here is some simple diagram to show the benefit. Okay. So here are some diagrams to show the benefit. Okay, let me just check everything is okay. Okay, everything is fine. Oh, because my alarm is just showing a lot. Okay, so you can see that in this illustration, simple diagram, it simply shows that the original latent diffusion model, the base model, is not styled and it's not fast. But if we are using LCM, of course it is fast, but it is not styled. If we are using a customized LDM, it is styled and fast. But we are training it, if we are training it with LoRa, because LoRa can work with each other. We can stack the LoRa to each other. So if we stack a LCM LoRa with a customized LoRa, together we can get a customized LCM. So that's another benefit. We can apply this LCM to any customized model that we prefer. Not just to the original Stable Diffusion, and we don't need to. If we wish to make a model faster, we don't need to do the whole LCM training, distillation training on that model. We only need to do the distillation on the original model, just with the LoRa. Then we can apply this LoRa to the other customized models. It can still works as well. So that's a key point of this LCM LoRa paper. So we have 3 papers here: the CM consistent model, the LCM, and the LCM LoRa. The original one is more original. It's lay the foundation of consistent model. Then the latency consistent model is apply the consistent model on a latent space. We know that we are working on a stable diffusion, not just any, because we only care about stable diffusion. But in general, it can work on any latent space. But this approach, this application is just trivial. The important contribution of it is to lay out a conditional formula on the consistent model. There are many ways to do that, but at least they give us one way that is proven working in the practice. That's very good. And the LCM LoRa is simply apply the LCM on using LoRa. And I think the contribution is the observation that and the experiment that prove that LoRa works very well in LCM algorithm. That's it. So here's the result. Using 4-step inference, it can generate pretty much very good result, and it can apply to different stable diffusion models. And here is one example of style model. The style model is a paper cut, so it generates the images in a paper cut style. Although they look different, but you can see that the quality seems to be pretty good, even with like 4-step or 8 steps. It works pretty well. Even with 2 steps, it is passable. Okay, so we have finished the first part of today's lecture. That is the 2 more generative models. The second part, aside from the homework is one thing. The other major part is the multimodal LLM, because it is also a very important trend in the generative models, generative AI. So I got in recently there was a Google AI event, which is one of the annual event of Google. for announcing their product and their achievement in AI in last 2 years. Google AI is more focusing on AI, and even more every year. So in Google AI, they are announcing in this year, in Google I/O, they are announcing the Google Flash. I mean Gemini Flash. The Chat GPT of Google is Gemini. Currently is Gemini. It used to be known as Bart, but the Gemini is a new Bart. So the latest Gemini is one of the interesting is Gemini Flash. It is a fast model, but it is also a multimodal model. We'll see a little bit later. And the revival of the Project Astro. It is very similar to the video that I'm going to show you very soon, which the OpenAI announced their GPT-4o just 1 day before the Google I/O beginning. And they actually announced a very similar product. Google like Project Astro and GPT-4o, they have very similar capability. They are different. And Google I/O, because it's a bigger event, they announced a lot of different things. But one of the things that people are interested in are very similar. Is Google, the Project Astro and the Gemini, multimodal Gemini, and GPT-4o is from OpenAI. And yesterday or the day before yesterday, Microsoft also announced the Copilot plus PC. We'll see it also very, very soon. But currently, let me first show the videos from the OpenAI. Let me click here. This is GPT-4o. So let me first to change the audio so that you can hear the audio from the video.
Hey, how's it going?
Hey there, it's going great. How about you? I see you're rocking an OpenAI hoodie. Nice choice. What's up with that ceiling though? Are you in a cool industry style office or something?
Well, can you take a guess at what I might be doing based on what I'm showing you here?
From what I can see, it looks like you're in some kind of recording or production setup. With those lights, tripods, and possibly a mic, it seems like you might be gearing up to shoot a video or maybe even a live stream.
Yeah. In fact, we've got a new announcement to make.
That's exciting. Announcements are always a big deal. Judging by the setup, it looks like it's going to be quite the professional production. Is this announcement related to OpenAI, perhaps?
It is. And in fact, what if I were to say that you're related to the announcement, or that you are the announcement?
Me? The announcement is about me? Well, color me intrigued. Are you about to reveal something about AI? Or more specifically about me as a part of OpenAI? You've got me on the edge of well, I don't really have a seat, but you get the idea. What's the big news?
Yeah, we've got a new model that can interact with the world through audio, vision, and text.
Okay, so you can see a summarize that at the end, they're announcing something that can interact with the world with text, audio, and video. So it's GPT, but it can see and it can hear. So from the video, you can see that it published. We're assuming the GPT can see the surrounding from the camera of the phone and doing some inference. And also, when they do the conversation, although we don't know the detail, but we're assuming that the GPT is actually hearing the audio directly. And when it generates the speech, it is not from some other independent, separate text to speech. It generates the audio directly. So that's what we call a multimodal. A model that does not only access to just one media, not just to text or just to image or just to audio. It can access and interact with both audio, both video, or just more than one media or more than one source. So that's what we call a multimodal. People are aiming from the things like GPT-4o. Let me show it in full screen. So we are going to make the AI not only to chat with us, it only can see and can hear and can speak. Or maybe incorporate with the diffusion model, it can also generate image or drawing like what we're drawing something. The project Astral has a video very similar to this one, and also people are using them. So one application is that I just seen in the Twitter. So you can see that it's May 21st. This is Microsoft. There are already some AI that can play games like Minecraft already. But this one, I think this is Microsoft using GPT-4o to, so when somebody is playing the Minecraft, the GPT-4o can do some command or doing some instruction. Like, okay, suppose you are a very beginner in this game and you have no idea what you should do. Probably we can let the AI to read a guide or walkthrough. So sometimes we are really stuck in a game. We read the walkthrough and read it line by line and to follow the instruction to play a game if we are really stuck at some point. But that makes the playing the game less fun because we are more supposed to work that by ourselves. If we are already looking the solution, it kind of spoiled the fun. So the AI can read the walkthrough or guide for you, and when you really need some suggestion, you can ask AI to do that. So that can only be implicated if the AI can see the things. So what Microsoft does is it provides a Copilot Plus PC that can look at the screen of the desktop. So because it can look at the screen of the desktop, it can give you some comment or suggestion because it can see the progress you are having. Like, okay, how many resources you have already collected. So it may suggest you, okay, maybe you should do next one. You should to build some X, so you can, or building some other tools, so you can go to mine more like the iron or to mine more the different kind of materials. So it can give you some suggestion, especially for a game that is more difficult more complicated. Another example is here. They use Gemini 1.5 Flash to guide to play the Mario 64. Mario 64 is one of the oldest 3D game, true 3D game. So in early game, there are less they're more challenging, and people are still trying out to experiment what a real 3D game should be. So for a Mario 64, it might be kind of confused for modern players because they don't know what to do in this game. It's kind of like an open world and it's open-ended and no specific goal you want to get. And sometimes the hint might be some kind of ambiguous because some NPC is talking to you, so you should collect something, you should help me to do something. But you may not understand what it is. So sometimes you need some help. And like the Minecraft case, the Gemini can read the screen to see the progress of what you are going, and can remember what you have already, where you have already visited. And if it had already read the guide, it may give you some hint. And it should understand the status what you are at, because when we need to solve some quest, they usually have some requirements to make the quest complete. So first, the AI should understand what material or what requirements you have already fulfilled, and how to get to fulfill other the remaining requirement, so that you can complete the quest. Okay, so that's one of the usage of the multimodal AI that people already know how. I think this one is not very creative. It's not a very creative because everybody knows. It's kind of everybody already know this type of application that people can do. Something like, okay, the AI can read a recipe, a cooking recipe for you. And if you have a camera to see you are cooking. So some recipe are writing in a more ambiguous way. If you have some questions, because some people are more familiar in cooking and some people are more novice. So for me, or for some people not very good at cooking, those instructions may be a little bit confused. Maybe some terminology we are not fully understand, or maybe something that we see something that we may say, okay, we are cooking something that seems to be not normal, and we may suspicious that, okay, this meat is already being black. What should I do? The recipe says that I should use a big fire, a full fire, and cook it in like 3 minutes. But after like 20 seconds, the meat is already being black. What should I do? There are many different questions we cannot ask the recipe, because the recipe is just some text written on a paper. However, if we have an AI, it reads the recipe. It can monitoring the progress we are doing. And whenever we have some question about maybe it is some common question, it says, okay, that's normal. We wish the meat to be black. Maybe that's the normal thing. Or maybe it will alarm you. Okay, you are doing something wrong. The power you are giving to cook meat is too more. Maybe something it can answer you. So that's kind of application we have already imagined. But I think there are more applications that remains to discover. There must be a lot of different applications that can be used for this kind of AI. Multimodal remains out to explore, and we expected people are doing a lot of things very creative using the multimodal large language model, just like people doing for the LLM already. And for now, this type of, you may still think this type of application is very creative, but for people already know multimodal AI for a while, these are just standard applications. I'm expecting something even more creative. Okay, so that's a simple explanation of what the future or what things you can, what application you can develop with this new technology. But at least the goal of this course, we are more interested in how to implement and how does this kind of things work. The current open source multimodal AI are more focusing on text and image. Although we are looking for something can cooperate with audio, video, image, text all together. But currently we are the model we are going to talk about are mostly limited to the image and to add in the image capability to the large language model. And the models we are talking about are limited to the models that the large we are restrict to the large to add the capability of the large that it can understand to see the image, not to generate an image. Because the text to image model can already be viewed as a multimodal model. Sort of, because it can take image condition and the text condition together and generate the image output. But when people are talking about multimodal models, most of the time they are talking about the large language model that can take image as input. But from the definition, we have already deal with the multimodal model already. Because like a control net, and because of the nature of the diffusion model, you can use image as input, and also we take the text encoded text as a condition. So we are already dealing a lot of the multimodal model. But right now we are dealing with the large language model that take both text as input and image as input, and it can generate text. Although the principles are pretty similar. So if you understand the principle here, it would be easier. I won't say trivial, but the principles are the same. You can generate the same thing to the audio input, video input, and also like audio output and image output, or not only text output. But right now we are talking about focusing on the large language model, and we wish to add the capability of image input into a large language model. So here, first we show the multimodal understanding, the benchmark. So you can see that the multimodal model that we are talking about, like GPT-4 vision, and so this is a rank, a leaderboard. The rows with green background are property models, and the rows with pink background are open source models. The currently leading multimodal model is still GPT-4 vision, but some open source models still have a very good quality, like a Vela, and I haven't seen yet, but the Lava, we are going to mostly going to talk about Lava, and also like you can see the E model, and these two are the Chinese model from China. Also, you can see like the blip and the instruct blip. Here we see a emu model, emu2 chat. This emu is not the emu image generative models that we covered in previous lecture. This is another one, not the one from Meta. This one is a multimodal model, although they share a similar name. But this one is more specifically called the emu chat. So if you are searching for emu AI model, chances are you are reaching to this one, not the one that we mentioned before. Just a note here. There are more models below here. I'm just clip it on the top models here. So we are starting from the model, clip model. We have already encountered this model before because when we use the text generative models, we are using clip as a text encoder in self-diffusion, in maybe Imagine or other models. Self-diffusion 3 also. The self-diffusion 3 use T5 and 2 different clip model. So clip model is one of the original multimodal model that connects the text encoding with the image together. The earlier models already have some image captioning models before the clip, but clip can be considered as a milestone that connect the image and text together. Although it is not doing the image captioning directly. So at the development of clip, it does not have many large data set of image and the text pair. So that's one of the contribution or things that clip does. So here are some datasets that we already have right now. This is from a repo called the image to dataset. You can check it here. It is a tool that you can download the image for this image text pair dataset. And here list a few typical dataset like Lion. It has 5 billion image text pairs. And CC conceptual caption. It has two conceptual caption model dataset. One is 3 million image text pairs, and the other contains 12 million image text pairs. If you go to the repo, you can only download the URL of image, not the image itself. It also only provide the URL of the image and the caption, the text corresponding to the image. You have to download image by yourself. The dataset itself is usually in a more open license, like a Creative Commons or public domain license, or something more you can use either in commercial or research. However, because when we wish to generate images, like you train a diffusion models, we will need the image itself. And when we train the diffusion models, because we are using it as a source of image to generate new images, so there usually has some copyright concern. When we wish to train an image caption or image understanding text model, language models, we still need to download the images. But as far as I know, they are less concerned to the copyright. But still, you need to download the images. And well, during your training, your model is going to see the images Otherwise, you don't have to download it. The reason you need to download it is because when you're training, you still need to read the information of the images. But as far as I know, there are not many concerning about the copyright of this the image capturing models or the models we are going to talk about. But for or maybe like the object detection models, they also need to use images and download images that you don't have the copyright to distribute it. But people are less concerned about the model trained about it. I think there are some concern, but as for the multimodal model, I don't hear much complaining, at least not as much as complaining about the like the Stable Diffusion or other image generative models, or like Sora. People are complaining about Sora or about audios. Recently, there are Scarlett Johansson issues about the OpenAI, because one of the voice when we use ChatGPT, we can ask the ChatGPT to have the voice response. So one of the voice that you can choose is Sky. It's called Sky, SKY, like a sky. So I think yesterday or recently, people are complaining that maybe from the sorry, the team of Sky behind the Scarlett Johansson, complaining the voice is too much like similar to the Scarlett Johansson herself. And also because Scarlett has voice over a very famous movie called Her, H-E-R. It is talking about AI assistants. So she is voice over for the AI assistant, and ChatGPT is also an AI assistant. So that makes things a little bit more interesting and complicated. But that's a thing. So when we wish to generate the image, video, or audios, I think these are more concerned about copyright. But when we are trying to not generate image directly or video directly, just to understand the image, they're still concerned, but much lesser. Okay, so anyway, you have to download the image, and just remember, although the repo says these datasets are Creative Commons or public domain, it doesn't mean that the image that you downloaded is also public domain. The reason that you need to download the image by yourself is because they are copyrighted, so they cannot distribute it directly with their dataset. They can only distribute their text, the text accompanied with the image and maybe the URL. Some people even argue the URL itself should have some, it is not ethical or not legally correct to provide the URL, because URL is considering as something maybe related, copyright related. Yeah, but currently you can download it, and they are claimed to be public domain or Creative Commons. So these are the datasets. Originally, they are like Coco or ImageNet. ImageNet is more about the bounding box and the labeling, the class labeling. But MS Coco has some. There are a lot of Coco datasets. One of them have 600,000 image text pair. Back then, it is already a very, very huge dataset, but now we have a lot of dataset that contains more and more like 3 million, 12 million, or even 5 billion text image pairs. So you need to consider that back then it doesn't have that much. So the paper at the period of CLIP or before, around the CLIP, there's still an issue to how to collect or generate the dataset. So what CLIP does is it has a text encoder and an image encoder. And because we have a dataset of the text and the image pair, we have text and image pair. We wish that the image encoder, the image encoding and the corresponding text encoding are sort of aligned. They are aligned, they are similar. So we have a metric here. Whenever you have image encoding and corresponding text encoding, their encoding are similar. Which their encoding are similar. When they are not from the same image text pair, from the text is from one pair and the image from the other pair, they are not similar. So by doing this contrastive learning, we can train image encoder and a text encoder that they are aligned to each other, so that when we take an image and text pair from dataset, the text encoding of the text and the image encoding of the image is very similar in maybe in cosine similarity. One of the popular similarity measurement is cosine similarity. So that's it. We are training this text and image encoder. So this one CLIP is very straightforward, but this requires a lot of data, and this approach has not. Here is the first one to do that. Although this may seem to be kind of obvious that, but no one has done this before. Mostly because we don't have such big. We don't have good text encoder, and we don't have a good dataset before. So CLIP is the first one to do that. Despite the principle seems to be a little bit straightforward and easy and simple, but this one, and also because people are focusing on image caption, so people might overlook the usefulness of this one. So it also provides a way to actually use the model trained by this method to use the CLIP model. So if we wish to do a classification of an image, we can first, for each class, we have a word here, and we use a text encoder to get a embedding for different class. And when we take a new image here, we can use the image to get its embedding. Then we simply compare the similarity between this embedding and this text embedding, and we can find the class of this image. So that's the usage. So you can see that it is an open vocabulary classification. It can do the open vocabulary classification. So this model is very basic but very useful. And later on, there are something called unclip. It is a generative model. So I've just put here that you know that there's a model called unclip and what it is. So we are not only talking about two generative models. So this is the third image generative model we are talking about right here. This is also from OpenAI. Unclip is something that clip is something clip have two parts. One is the text generative, it's text encoding model, and the other is image encoding model. So unclip can be viewed as the unclear part, the inverse part of the text encoder, and the maybe image encoder. So basically, it takes the image text encoding and it wish to generate a corresponding image. So what does this sort of like just the text to image generative model? Yes, it is. But what is the difference between this one and the other diffusion model? Because Unclip is also using diffusion. Okay, the thing is that first of all, it uses the clip to generate a text, encoded text, and use the clip to generate the image latent. So you get an image encoding and a text encoding and the image encoding. So instead of use this text encoding directly, just like the Stable Diffusion or other diffusion models, it first uses the diffusion model or any autoregressive model to generate the image encoding from the text encoding. So the spatial part of the Unclip model is it does not use the text encoding to generate the image directly. It uses the image encoding to generate the. It uses the text encoding to generate the image encoding by using diffusion model or other generative models. Not just use this diffusion model, but it uses a diffusion model to generate the image encoding from the text encoding. Then it uses another diffusion model as a decoder to generate the image from the image encoding. So that's what Unclip does. It does not generate the image directly from the text encoding. It uses because Clip has two types of encoding. One is text encoding, and the other is image encoding. It generates the image encoding from the text encoding, from the given text encoding. Then it uses a decoder to decode the image encoding from the text encoding. From the image encoder. So it can be considered the inverse of the image encoder. This one, decoder, can be considered as the inverse of the image encoder. And also, it has a generative model to generate the image encoding from the text encoding. Also, that's the Unclip model. So that's an interesting idea. And after the clip, we also have a blip model. The blip model is a little bit more. There are two blip models. One is the blip 1, and just call it blip, and the other is the blip 2 model. These two models come from Salesforce. Salesforce is a famous company, and it has also researched a lot of AI research. So the first blip model, the primary contribution or the focus is on the unified visual language understanding. So it is a multi-text model. We have a transformer. We have a transformer here. So these are transformer blocks. But it also do in text encoding and image encoding. But it doesn't unlike the clip, it does multiple texts altogether. So first one is the image and the text contrastive model, kind of like the clip. Also, but it uses a text encoder, and it goes because the text has different text, so it has a prefix to indicate what text it is going to do, like an instruction. So we are going to, by given this prefix, we know that we are going to encode something, and we are going to do the class, to do the ITC contrastive things, and do the encode and doing image and text matching, and there's a language model. So ITC is a contrastive learning. The text is going to an encoder without any inference from the image. And the image is going into an encoder without any inference and any information from the text. So we get two encodings. We wish them to be match or similar when they are from the same pair, but they are different from the different pair, if they are from a different pair. Also, that is very similar to a clip. And the other is the ITM, which called the image text matching. So it is generated to the when we fix it, is more like a classification task, sort of like this one, but in this one it takes two input. One is the image and the other is from the text. The objective is to tell does this image and this text are from the same pair. If they are from the same pair, they will output the yes, it's from the same pair. If they are not, we output no, they are not from the same pair. So this is a binary classification task. So you can use cross entropy as a loss or other things, any loss that works for the binary classification. And the last one is language model. So it generates the caption. So for example, if you input this, it will complete the sentence. So input a question or a query, or maybe in a prefix of the sentence, it will do the caption or text completion. Also, this one is a language model. So it unifies everything and do a multi-text to train a more. So one thing is because it is multi-text, we can utilize in the dataset more efficiently. So each sample will do multiple training, different goals. So usually it will achieve a more better quality models. The other thing is because we are doing it multiple for multi-task, it can actually use for multiple task. If we are only doing for the clip, it cannot do the image captioning. But because we have a language model here, it has ability to do the image captioning. So Blip can do image captioning and can also do similar things as the clip. So here are some the training procedure. I think this is one of the most interesting and most things that you can, most valuable things you should read from this paper. Because although, like we say, we have a lot of huge data set, like Lion 5 billion, like Lion 400 million, or like CC 12 million or CC 3 million. A lot of large data set. But the quality of this data set is not good. You can imagine that how much cost would it be to have people to write the caption or write the annotation of all this for a text or for each image. There are 5 billion text and image pairs. How many people and how much time are going to do for that? What is the cost? How expensive that would be? So what they are doing is doing something more automatically. Like when they crawling the web, they are kind of using some heuristic to extract the text, maybe around the web page or things like that, so that they can get large number of image and text pair. And maybe people are some human are used to annotating some things, but for that large of quantity of image pair, it is very difficult to monitoring the quality of the image and text pair, even if you are asking people to do that. You can imagine you are paying people to do the things like, okay, for each image and the text pair, I'm going to give you maybe $1 or $2 or $10 maybe. I don't know the price. I have no idea. So that can be way off the realistic situation. I don't have an idea, but just say I'm giving you $1 for each text and image pair. So if you are the annotator, you are going to annotate as many image and text pair as possible in the at least time as possible. So if you can do it like 1,000 image and text pair in 1 hour, you will do that. If you can do that in 1 minute and doing like 10,000, you will do that. The quality is not the most important thing in your mind. So if you are asking people to do that many image and text pair, they are going to do a lot of things very sloppy, very bad, very poor qualities. So there are really a lot of image and text pair that are really bad. Just like we have already seen in last week, the email or like stable, I forget, but one of the important paper that one of the paper that I present last week is focusing on the quality of the text and image pair. But recall that they are doing that is using synthetic text by using bleep. They are using bleep itself. But this is a bleep. We don't have that yet. We cannot use bleep to generate better quality text unless we already have a bleep itself. But can we actually using bleep to training the bleep to help us to have better, improve the quality of the dataset and the training bleep? Is it even possible? They are actually doing so. They are doing this called dataset bootstrapping. They are training a model and using this model to kind of filtering the text, grounded text encoded. They are going to filtering the image and text pair, and they are also using the captioner, the training captioner, to improve the quality. And after you have a better quality model, you do it again. So that doing the bootstrapping, they can do that. So that's the most interesting and something that the most valuable things that you can see that in this paper. So this one is very interesting because we all know that things we should do that thing. As I might be mentioned before, when we get a data set, you are going to assume that the quality is not good. So you first need to do something to do a filtering, or to find out which part does not have good quality, and to maybe ask the labeler to do labeling again, or maybe just filter out some part of the dataset that we don't want to use. However, it is not always easy to do, and to do it do it right or do it in the best way, because sometimes we use some heuristic and it does not doing very efficiently. So it is always good to see people has some already working practice or method, so that we can have a reference and maybe learn something from their procedure. So this one is I think is most valuable and very interesting. This one is simply multitasking, but also multitasking is another thing that we know that is good, but it's not very easy to do it right. So Blip is really provides some really good experience about something that is we know we should do, but it's not easy to do it correctly. So that is the most valuable things that in Blip paper you should read in it. And they have a Blip 2 and also come from the Salesforce research. So the Blip 2 is also the same, using the same thing, but it is doing it using a Q-former, a Curie transformer here. Focusing on here, it is a Curie transformer. So what is a Curie transformer? It has a frozen image encoder and a frozen large language model. And it is focusing on the, so when we have an image encoder and when we have a large language model, so there are a lot of this kind of thing already existed. And they have used a lot of GPU to train them. So the Blip 2 provide a bridge so that we can combine these two already existed pre-trained model together to become a multimodal model by using a Q transformer to combine them together. So the more abstract way, more overview way is that by frozen these two image encoder and the large language model, the Q-former is the transformer that takes condition of a query and the text and the images here. And the output is fed into a large language model and it can generate more images. So what is the, so this one is the image here, and this one is a text input query here. So you can, the output of this one is right here, like this love is like a sunset. So it is already a way to add the ability to make the library have ability to see things. So this is Blip 2 that Blip 2 can do. It is also like the Blip 1. It has 3 different objectives, like the contrastive learning, like a binary classifier, and another is a like a language model, like a language model. So it's still using a unified way and using a bootstrapping way to do the training. But the thing is that I think the model is more unified than before, and it has a Q transformer. So it only modifies the self-attention part so that everything can works like together. The self-attention takes the queries and the input text all together. The query and the text together. But by just modifying the mask, what I was saying was if you want to do the self-attention, there must have to be a self. What is a self? The self is a query token and text token all together. They concatenate them together to as a single self. You feel like them as a whole self. And because for different texts, we only need to adjust the mask. So other than that, we can share everything together. They simply have a different mask. So for the contrastive learning, the mask as the query goes refer to, can have attention to itself, and the text has attention to itself. They are not all together. So it sort of have two different paths. The query has its own encoding. The text has its own encoding. And for the image text matching, they don't have any things maxed out because it is a binary classifier. We're considering query and text all together. And for the text generative things, the text can see the query, but the text can only see like autoregressive things. It can see previous text. So kind of like that. As you can see that in this phase of training, this stage of training, there's only the image encoder. There's no text encoder yet. Okay. But here we have a large language model as a decoder. So depending on your large language model to be encoder-decoder based or decoder based, it has a different way to fit the output of this Q format into it. But they are pretty much the same way for training. So basically, if you see here, you can see that the Q format is a way to add image as a condition into a large language model. So here are some sample result. Like, okay, tell me something about the history of the place. So it can have some answering. It's okay, it's fine, but it's not the best result we can get so far. You will see it later. We have a lot of more advanced method. Although this one is like 2000, like after 2020, maybe 2021. It's not exactly an old method, but because this field has been advanced a lot and very rapidly, so there are a lot of new methods and improve a lot of qualities. So these results are fine, just fine. But you should remember that we are only using a dataset that has a caption as output. We have only image and the text pair, and the text are only just captions of the image. They are not exactly for a text of like chatting or question and answering, not for QA or like chat. Right now you might think, okay, so what we need is some like instruction fine-tuning, just like for language model, because we only have something like raw text, not the instruction fine-tuning. So we should do something like instruction fine-tuning or like chat fine-tuning. Yes, that's exactly what people are going to do next. Okay, so this one is LLM, visual instruction tuning. We are doing this kind of like the thing before, but LLM is in fact a little bit simpler. It is a more baseline model, more like a baseline model. It's probably is more advanced than LLM. LLM is using more simpler architecture. But the key point is here, it is using a way attempt to do the visual instruction tuning. So it is going to construct the a dataset that from the original captional dataset to become an instruction dataset. Also, that's the main contribution of LLM. So what dataset we already have? One is the caption dataset. It only has provided a description of the image, and the other one is the object detection dataset. It has a class and a bounding box things. So the idea is that we construct some instruction or question and answering things from this type of dataset. So how do we do that? What we wish to have is, at least for Lava, is first one is the conversational type of things, like question, what type of vehicle is featured in this image? And it answers the image features a black sport utility vehicle SUV and describe what the vehicle it is in the picture. And the second one is a detailed description. The instruction is ask it to have a detailed description. This might be easier because we are assuming that the caption is a detailed description. But we can add an instruction like, please describe this image in detail. And the answer is the caption itself. And the response type 3 is complex reasoning. Like, what challenge do these people face? And maybe something like what is in the right, because we have the boxes, the object detection dataset, we have bounding box of different things. So we can ask what is on the right of something, what is above, behind, or on the left of something. Maybe we can have something like that. So it is actually construct the dataset from this context, from the dataset we already have. So how do we exactly to construct this type of thing? This one might be easier because we can directly use in the caption. There are many different ways that you can do that. Like if we have bounding box, we can do the type of the position question, like what is on the left of this guy or something like that. So you can imagine there are many different ways to construct such dataset. And maybe you can think about some clever way to do that. In Lava, it uses the GPT to help to generate these things because we already have some text models. So these are text, and we can write this in a text format. And we can ask GPT to generate this desired text in our the text format in the format that we want. So that's the idea. Although we are not using the ability of, like we say, that GPT-4 vision can actually see the images, but we are not using GPT-4 vision to, because that's a cheat. We are trying to develop the vision ability for a large language model from scratch. So if we are using a large language model with vision ability, that's a cheat. That's cheating. We're only using a text ability because image has a corresponding text, although they are not exactly in the format that we want. But we can ask a language model to reference to this text and to generate corresponding questions or conversations by giving these informations. So that's the idea. So they generate like 158,000 unique language image instruction following samples. And these are numbers in different categories. So they have 3 different categories. They try different approaches. This one is the best approach they got when they develop in the Lava. But for the user, the term of the usage of the GPT-4, it strictly forbids people using the output of their ChatGPT models to train other AI models. if you are not getting permissions. That's reasonable because they are AI companies. So they don't want the other people to use their service to train their own model, to take money, to take a market from them. So they strictly forbid people to use their data to train other AI models. So that's why they banned some connection from some companies, AI companies from China, like the MUSE. I think not only from China, but I remember that one instance is for China's company. But if I remember correct, this is not the only case. Some people are using the queries from the ChatGPT, and OpenAI assume they are, or at least they think like they are using it to train their own models. So they suspend their connection to the GPT API. So in this case, Lava is using, I believe they are asking, they have their permission to train this one. So if you ask it nicely, they can use their data to train things. But the thing is, Lava is not up to commercial use. You cannot use Lava to do any commercial. So you cannot fine tune Lava, or because they are using the GPT-4 data. So although the weight of Lava is public available, they only use for the research purpose, because they are using GPT-4 generated dataset, and this is their method. Their core method is using GPT-4 generated text. It's a clever way. You can use other language model instead of GPT-4, like using Llama, Llama 2, Llama 3 to do the same thing. But for the Lava per se, because they are using GPT-4 generated things, it is forbidden to, it's forbidden to commercial use or any other usage other than the research purpose or evaluation purpose. The model of the Lava is pretty simple. It has a 407 fission encoder, like FIT L14. You can use any, but it uses FIT. And it uses a language model. It uses the Vicuna, because back then, Vicuna is one of the best fine-tuned, customized model from Llama. So they use Vicuna. A lot of models are based on Vicuna. A lot of models are fine-tuned from Vicuna. And Vicuna is a Lava, I think, 1.5 based model. Okay, yes, Llama 1.5, not Llama 1, not Llama 2. If I remember correctly, I am not 100% sure, but Vicuna is, let's just say Vicuna is a fine-tuned model from Llama 1.5. Because it already provided the recipe of how to fine-tune it. So the Lava itself can be considered a special case of fine-tuning Vicuna. It's using the exact recipe of fine-tuning the Vicuna model. The only thing that's different is, okay, let me make it clear. So the fission encoder is frozen. The language model is not frozen. It is used for fine-tuning, but the fine-tuning procedure is very standard. It's just like other fine-tuning for language model. People are very familiar with that. So although it is not frozen, it is not a big issues right here. It's just fine-tuning a language model, and the recipe is exactly the same as a Vicuna, like the learning rate, the scheduling, or anything. The only thing that added and combined the fission encoder and the language model together is they have a projection W, which is a linear layer. It's just a simple trainable linear layer. This is not a trainable. This is trainable. It's just fine-tune, standard fine-tune. And the only thing that is special or new is here. They have a linear layer. But linear layer is just so simple because you can see that in clip and in the blip case, they have some more for more complicated, more like using a transformer things in there. But here it only uses a projection. And it's called projection. It's just a linear layer. So it has a linear layer to map the vision encoder things into a token that can be feed like into things that can be fed into a language model. So it's kind of like the blip, at least for the blip, like blip 2 in the spirit, although they didn't fix or frozen the language model, but it also gives a bridge between the vision encoder and the language model. Its bridge is very thin layer. It's very baseline. It's just a linear layer. The only so I say the core contribution, the core part is it's just the dataset construction. They use GPT to construct the dataset. But I actually like the approach by using a very baseline model first. At least they actually call it baseline. So there's nothing wrong with it, although it is simple. But I like things to be simple. Because you have to start from something simple. And this one actually just work. Okay, so that's it. So that's pretty much it. But when training, it also have two stages. The first one is they still using the captioning because their contrast model only have, I say only have, but it's a large line. But compared to other models, it only have a relatively slow number of image and text pairs. It only have like 158,000 image and text pair. So it would be nice if we can to do a more, just like we do the language model, we first do a non-instruction, a base model. Then we do the instruction fine-tuning. So at the first stage, it train it on a more general, a larger data set. So it filled out the CC3M because we still need it to be fairly high quality. It has about 600,000 image text pairs. At this stage, it doesn't aiming for the question answering or instruction following ability. It more like we should let the image and the image encoder and the language model, we want them to be aligned using our linear layer. And the second stage is to do the instruction fine-tuning by using the 158,000 language image pair. Or it has two different versions. One is using that one, and the other one is using a science QA dataset. So they actually have two models. One is multimodal chatbot, and the other is science QA. Also, it is an existing dataset. So all of them is just quite a baseline. But sometimes the baseline is pretty good. So this is the result. This image is used a lot in demonstrating the ability of multimodal language model like this one. So this one is a image that's showing people do some extreme sports. This one is called extreme ironing. People do the ironing behind a car. there was a competition. Although it looks like absurd and like you may think it is a joke, but in fact it has a competition of this one. This image particular is used a lot in a lot of different papers by showing their ability for image understanding as a typical standard example. So here's a result. So what is unusual about this image? It has some very good response, and this depends on what happened in this scenes. It also has a pretty good response. By comparing it to GPT-4 and the Blip 2 and another model called the Open Flamingo. This is also another model that can do the things. And image understanding generally hacks. Also, we didn't cover it right here. Another interesting approach is mini GPT-4. By comparing to the Lava, it uses a more complicated encoder like Q-former, like in Blip. But it also constructs some datasets, kind of like Lava. But the only interesting part in here is using Q-former instead of just one linear layer. It uses Q-former and the linear layer. But I don't think GPT-4, mini GPT-4 much better than Lava. Although Lava is pretty simple, but it is not, at least it is not significantly better than Lava. In some benchmark, it is even worse, but for the case that I tried, it's okay. But it's definitely more complicated architecture. And in general, it is not significantly better than the simple architecture like Lava. There's no direct comparison because they are using different datasets. They are kind of developed in parallel. So this is not definitely saying that complete architecture like Q-former is not better. It's just saying there are not a lot of different factors that affect the final result. And in this here, mini GPT-4 is kind of trying to, this one is after GPT-4 vision. It tried to reproduce something similar to the GPT-4 vision. So it is in parallel with Lava, but I think the lesson here is that the takeaway here is that more complicated architecture is not necessary. I mean, it's not directly or immediately influence to the quality of the model you generated. There are many different qualities, factors. So maybe you can, so my way is always you stick with a simple model first and tuning other factors to make them right, like filtering the dataset, or like here, they filtering the CC3M to like here. This one is more important than the architecture, or like using transformer or convolution or MLP. This one is far more important. And this one is far more important than the other thing. So you may start with a simple architecture to leave less room to make mistakes. Because if you are trying to implement such thing like as complicated as this one, there are many opportunities that you can make mistakes. So I will start with some simpler architecture and try to do everything correct. Then just like I said, the final resort is kind of like a final resort, last resort. This one is more like a last resort. It's not the last resort. It's just we do this in a later stage. There are a lot of things you need to do before you are developing a more complicated architecture. Another thing you need to notify is that it uses Vicuna. Also, it uses Vicuna. But I didn't remember it very clearly. But as in these pictures, it's frozen. So that's another difference because it's not going to do it's not doing the fine tuning. It's only do the kind of domain adaptation here. Another way to use the Q former is instruct belief. Because it is instruct belief, so it also uses the Q former. So it's one of the models that you have seen on the list of my the leaderboard I showed before, the multimodal language models, language understanding leaderboard. So this one is instruct belief. This one is not from the Salesforce research group. This one is from Singapore and Hong Kong. Oh, okay. So this one is also from Singapore, but I think they are also from the Hong Kong and I was more focusing on the Singapore and Hong Kong. So, but apparently it also has a contribution from the Salesforce. So this one is called the instruct belief, and this one is the AVIS contains a lot of reports that are very interesting. But you can see that it has a lot of different reports that doing similar things. So it indicated that it's a really large research group. Okay, so what does it do? It collects the as the same. It collects a large data set. So you can see that it's typically we have different data set like Coco caption data set and QA data set. Right now we already have several QA data set already. Featuring QA, many of them are featuring QA data set. And the science QA, it collects a lot of different data set to do the instruction fine tuning. So basically, it's just the instruction fine tuning for a belief. Doing the instruction fine tuning for a belief. It's still using a Q former, a belief too. It's still using a Q former and do the instruction fine tuning. So the result is very good. In my experience, I think it's one of the go-to models for this kind of text, at least for some time period. I still will use this one, but because the field is rapidly improved, so I'm not sure. I still every time I do a similar task, I still do a survey and try some new models to see which one fits better. But this one is one of the go-to models I go. So the instruct belief does what it does is, so here are some examples that is provided in a paper. This paper are used to demonstrate the strengths of this model. So this one is the result of the instruct belief. Comparing to GPT-4, Lava, and the mini GPT-4. Everyone seems okay for me. You can see that maybe mini GPT-4 is a little bit behind the other models, but all models, some models respond longer text, and some like GPT-4 reply shorter. But everyone, I think everything goes pretty good. And this one demonstrates the strengthness of this model, the instruct belief. It asks, do you know who drew this painting? The instruct belief reply is Leonardo da Vinci. Although this one is shorter, but shorter doesn't mean it's worse, because when you ask this type of questions, you are expecting a clear and direct answering. For this one, it is very long. Although it might, yeah, here you can see that it replied correctly, and here it replied correctly. But still, this one is just too long. This is the information we are asking for. So the brief argue that it has better in this scenario. And when you ask something, if you wish to have a longer answer, you can say like that, introduce me this painting in detail. So all of them are, they are also mini GPT v4. Mini GPT-4, not mini GPT-4. But mini GPT-4 has a, you can check the paper, it has a very, the more poor answer in this case, but longer. All of them are pretty long answer. But the thing that the instruct brief claim that their strength is their answering is more factually correct, because it has answering the name of this painting, the girl with a pearl earring, and it answering the painter, and created in 1665. The lava only reply it's a woman in a headscarf, possibly of Dutch origin. So it claims that Instruct brief claims that their method of training can incorporate more knowledge of the large language model. So it knows more than Lava. And the GPT-4, okay, the mini GPT-4 only reply some garbage, very poor reply. It doesn't provide the result from GPT-4, like here. I assume that GPT-4 answering it pretty well. So here are some datasets that is used in the Instruct brief. You can see it uses a lot of different, all models, later models use a lot of more and more dataset and making them much better. And here are some examples of their corresponding text caption to it. And when doing the OCR, because some of the image dataset is OCR, that is, they have text and the text part of, there are text in the image, there are text writing in the image, and the text part is about the, it's not describing the image, but it's about the text that is writing in, appears in the image. So there are some OCR dataset. Let me check. I didn't see OCR right here, but usually they are using some OCR. No. I don't see the OCR dataset. But maybe you can see it in here. No, because there are some dataset that has a name. Like this here, OCR VQA. There are OCR here. So, except for OCR, they are using OCR. They treat OCR things differently, because OCR dataset and other dataset are kind of different. For the OCR dataset, you probably only need to read the content of the in the image, but for the other dataset, you are try to understand the things appears in the image. So that's a little bit, I think, orthogonal, and they are kind of orthogonal tasks. So they treat the OCR. It is usually a very standard way to treat OCR and the other image in a different way. Mini GPT v2 is a successor of the Mini GPT-4. It claimed to have a better performance than Lava or Instruct brief, and I don't know this model, Shikara, but apparently this is another multimodal model that has very capable considered to be very capable at the time. So Mini GP v2, the special point of Mini GP v2 is that it is a multitask training. It constructs a dataset to be a multitask, and it trains it in the multi-objective. So what does it mean? So the architecture is not that interesting. It just use a linear and concate everything. So it seems it use a simpler architecture like Lava, but it doesn't matter that much. The key point is that it is using a multi-task instruction training. So for a pre-training case, they use a lot of different datasets, and they have multi-task training and the multimodal instruction tuning. They do a lot of tasks. The key, the most valuable part is it is very creative to use dataset and create different tasks. So it combines the object detection dataset and combine the caption dataset, combine the OCR dataset, probably that's all, and some QA dataset, and combine all of them together and incorporate them into like 1, 2, 3, 4, 5, 6, 7, 8, maybe 8 different tasks. So it has some adapter in the dataset creating procedure. So for each dataset, it can create different type of task for that dataset, like QA, like I'll show you here. So for example, if we are coming from something like object detection, it has a task called detection, which directly do the object detection things. But you can ask it to do to specify the class. It need to do a detection like do a detection like a lamp here, or like so it's more like a open vocabulary object detection. You can do that. Although it only has a very low resolution detection, I think it's 100 by 100. You cannot do further. It has some illusion that it can work on a high resolution image, but the object detection resolution is 100 by 100 only. And it applies to all of them. And another thing is that it can do the grounding. Please describe this image as still as possible. It can show that it has a fruitcake here, a coffee, a cup of coffee here. So by using the object detection dataset of bounding box and class, you can create things like this one, the grounding task, and it can identify tasks. So if you in the input you use a notation tool to square to have to bound this bounding box here. You can ask what is this. It's kind of using the dataset the other way around, because when we do the object detection, we are using an image to predict the bounding box and get the class of bounding box. But here it treats the bounding box as one part of the input. The part of the input, and then you get things like output the class. Of course, it has a template. It does not say it's a blockchain chaining. It will have a template saying, okay, it is a blockchain. It is something like this one. And as here, you can see it clearly that it has 35, 45, 65, and 70. It does this is a coordinate of this bounding box. Because like I said, the resolution is can only up to 100 and 100, 100 by 100. So you can see everything is here is like under 100, 2 digits number. And it can do the VQA, like which country does it come from, like this type of VQA. And it can do, you can see that it has a prefix to specify the task it's going to do. And it can also do freeform QA. So these two types of things. And it can combine all the information together. Like you can imagine that we can ask what this people is. If you have a face recognition, or like you can do if you have a bounding box of here, and you can use another like blip or things to extract the caption of this one. You can identify which people is which people. And you can ask, in this picture, it asks what the right player's head, and it can find the right player. But in original data form, it may have a bounding box of these people and a bounding box of a head. And you can construct a question and answering things like this one by using the bounding box information to construct things, to construct many different type of questions, or like what is the people in the middle is playing, something like that. So the contribution of this GPT-4, GPT-v2, is to construct this dataset in a more variety way. So that's the interesting part of this one. And it claims that by using this method of training, it will increase the ability of the image understanding for large language models. My experience is that this type of base model seems to have a better, can reply more factual result because it is trained in this way. So maybe that's a fair assumption, that because it more focused on the more precise answer. So by comparing to the Lava or other models, if you wish to fine-tuning this kind of model, it's usually very easier to ask it to answering the text in certain format. But it's difficult to ask it a yes/no question, or some question that like for a very specific answer. But mini GPT-4 kind of like, mini GPT-v2 kind of like interpret works better in this yes/no answering. But I haven't done a very large scale study. It's just from my experience, it's kind of works better if you wish to make this model more to have some real work, real jobs in practice. So for at least it works better to do object detection. So that's some real work that it can do, not just describe the things for you. For describe things, they always do a pretty good job. This one is a Lava 1.5, the new Lava thing. This does not change a lot from the original Lava. Pretty much the same. It only have two different. One difference is that it uses a higher resolution image. In the original Lava, it takes the picture 224 by 224. So the resolution is only 200 by 24. So for the text that require more details in the images, like UI, people want to do an AI agent to help you to control a UI or design a UI, to writing code so we show the markup screenshot and we can ask the AI to write the code for us. There's some demanding popular requests for these multimodal language models. Those things are related to UI. If something are related to UI, it requires more high resolution details. And in some situations, people are like the surveillance camera or something. Most of the time, you require some high resolution UI, higher resolution images. So this one is training for high resolution images. And it also adding academic task-oriented VQA. Just kind of like the in-charge blip and like the mini GPv2. If we wish it to be more, have more ability to do a reasoning, to have more logic, usually you need to have some data set that to contain more serious logic and more serious reasoning task, so that it can understand more. But in here, instead of using multi-text, it's still using a VQA dataset. It's just the content of the VQA dataset is more serious, or like the academic text oriented. So like, what is the distance between moon and the more maybe like the geometry QA things. So they are more serious questions, not just more diverse questions like what is strange things about this image, what the hat is wearing, what color is the hat of this guy wearing. Not this kind of simple question or casual question. It's more serious, more require more reasoning. And for even higher resolution, it uses a strategy to decomposition of a higher resolution image into 4 and using resize to have a low resolution image together. All this together to fit into the large language model so that it can understand the detail and the whole picture. So with this detail and similarly minor change, it increases the ability of the lava a lot. So you can see that it achieves much better result and comparable to other SOTA models. And it claims that it uses less training data. So that's the result. I think there's no definite conclusion of which architecture is better. It might the thing that it uses less data, it might be contribute to, I don't know, because it is doing a fine tuning. But maybe different factors. But at least we see that Lava provide a recipe that can use little training data to achieve a higher quality result. And also it observes immersion or generalization capability. Because the dataset only provided in English, like every image and text pair, they are only trained in English. Of course, the language model itself is trained used with multi-language, because it is based on Lava. I think it's based on new Llama. I think this one is based on maybe the Llama 2. I'm not sure, but it is based on Llama, and the Llama can do multi-language things. So although the image understanding is only training on the English with image pair, English text and image pair, but it turns out you can ask the question in different language and it can reply you in different language, like in Spanish, in Japanese, in Korean. And I assuming that it can, in fact, it can do the the image efficient QA in any language, kind of like ChatGPT-4. You don't need to worry too much about languages, which language you are using. It can transfer to other languages. Now, this is a very common situation that observed in many different models like this one, multimodal like this one. Okay, so that's about today's topics. So the summary, the takeaway is that we're introducing a different concept of how to add more capability into a language model. Although the language model, large language model, is designed to only take text input, but the text input are simply just a sequence of vectors. So if you can encode anything into a compatible space in a tokens, in a sequence of vectors, then you can make large language understand other type of things. Either like here we show in the image, but the same principle apply to other things like audio, like maybe in videos, or maybe if I'm getting more creative, maybe you can take if you have a Internet of Things, like you have a lot of sensors, maybe it's a pressure, temperature, or other kind of sensors. It is possible that you use a similar way to adapt the input into the space of the input of the language model. So it can take them as input and do some reasoning for you. But the key point is you have to construct the dataset in a way that is reasonable so that you can train in the dataset. And you need a considerably large dataset, something like 100,000 like image text pair, or if you are doing audio text pair, maybe something like that. So needed to be creative, and then you can apply the large language model to a more wide usage. And although we haven't covered, and this is why our homework is asking you to construct the dataset, because these skills can transfer and apply to different areas. The ability of constructing dataset is crucial. Another thing is, although we are only talking about the inputting, understanding of other type of input, the similar principle can apply so that you can generate things. So you can generate images, for example. Although we already have diffusion models, so there are some obvious and apparent way to integrate a diffusion model or other text-to-image generative models with the large language models, so that you can have a model not only it can reply you in text, it can reply you in images and in videos, not the way that it is in like ChatGPT-4 or like in Gemini, because currently they are simply using the function calling method. They generate some prompt and feed it into other text-to-image generate models. Maybe you can integrate it into a single models, but the thing is, you have to think beforehand, what is the benefit of the strengthness of doing so? One example is for the audio. Because if we are using a speech to text or text to speech incorporated with a large language model, we are losing something like the emotion. So if we integrate them all together, the large language model can choose which emotion that it wishes to express itself. Kind of like the video we show in the OpenAI GPT-4o. You can see that the response is very human-like. And also for the input part, if you are only using audio to speech to text procedure, the large language model only knows the text. It doesn't take the hint from the emotion in the speech, the tune in the speech. So when combined together, it has a potential advantage of understand things not only from text, but also from the tunes or emotion in the speech. So if you have some, you can do some analogy to the images and to see the benefit of using it. Okay, so that's all for it, and I hope you find these materials we are talking about useful.